Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. The science of chemistry is pretty incredible because it's the science of everything. Stars and computer hard drives and desks and our bodies are all made up of different arrangements of atoms that are bonded together, breaking apart, or reacting with each other all the time. We already did a crash course about the wonders of general chemistry, so this course will focus on just a slice of that pie because we're talking about organic chemistry. And organic chemistry is the study of molecules that have carbon atoms. With 4 valence electrons, carbon often catenates, which means it bonds to itself. So it forms lots of different compounds. You can get long chains of carbons and hydrogens like dodecane, or rings of carbons like anthracene, or complex structures with multiple rings in other atoms like the steroid estradiol. You might think that the whole focusing on carbon thing would rule out a lot of the universe. And it does rule out things like glass, rocks, minerals, and gems other than diamonds. But organic chemicals are pretty much everywhere. Over these 50 episodes, we'll discover new reactions, new compounds, and new methods to understand them. And all of these discoveries didn't just appear in a chemistry lab notebook overnight. They're the result of centuries of hard work, isolating chemicals, trying to figure out what they do, and stumbling upon happy accidents that led to revolutionary ideas. A big part of understanding organic chemistry is grasping the logic behind everything from molecular structures to chemical reaction mechanisms. Even though these kinds of problems can feel overwhelming, treating them like a puzzle can help us make sense of them. So let's start our story with the birth of modern organic chemistry, which begins right around the mid-1800s. Plants like willow, ephedra, and poppies were known by ancient civilizations to have medicinal benefits, but they had no idea why. In the early 1800s, there was a breakthrough in understanding their medicinal properties, and people began to extract therapeutic chemicals from them. Today, we know these plants contain medicinal organic molecules like salicylic acid, ephedrine, and morphine. Organic means derived from living things, and the term organic chemistry was coined by the Swedish chemist Jens Jakob Berzelius, who discovered several elements and came up with the modern chemical symbols that we use today. At that time, organic chemistry referred to the study of chemical compounds extracted from living things. We thought that organic compounds could only be harvested from living things, but not made. That's why we used to dye our fabrics beautiful colors using organic plant materials, like flowers and dirt, with a little help from our own urine. Urea is the main nitrogen-containing part of urine that comes from our body's metabolic breakdown of proteins. But it's also a great fabric dye, mordant, which is a chemical that makes the dye last longer and often enhances the color. This is because urea can form a chemical bridge between the dye molecule and the fabric, and it shields the dye from fading. There's evidence that urea was used by ancient civilizations as a dye additive, particularly for indigo dye, the same dye that makes our jeans blue. In ancient Rome, people would even sell their urine to dyers to make some money. It was such a big business that the government even passed a urine tax to get a cut of the profits. If you've ever tie-dyed a shirt, the colored dye solution probably had urea in it too. But don't worry, since we've moved beyond the get every chemical from living things days of organic chemistry, it's not derived from urine. This urea is synthesized from an inorganic compound. And for that, we can thank German chemist Friedrich Wöhler. He was a rock collector and is credited with being the first person to isolate the elements yttrium, beryllium, and titanium, and the first person to discover organic matter on meteorites. But he's most well known for his discovery that an inorganic salt, ammonium cyanate, could be used to make urea without a living organism. Wöhler's discovery in 1828 is considered the starting point of the modern organic chemical industry. And today, organic chemistry is defined as the study of the structure, properties, composition, reactions, and preparation of carbon-containing compounds. This definition includes chemicals extracted from living things, but also man-made polymers like plastics. Throughout this course, we need to remember this one simple thing. Organic chemistry is carbon-centric. Carbon is the key atom in all these molecules, and carbon atoms do some very predictable things, like make 4 bonds. Keeping this in mind, there are several different ways we can draw organic compounds. One way to represent organic molecules is with a Lewis structure, like the ones we drew in Crash Course General Chemistry. Lewis structures illustrate what atoms are connected, and they show all the bonds and lone pairs of electrons in a molecule. For example, propane is a common fuel for home heating and barbecue grills, and it's a simple organic compound. Because we haven't learned how to name compounds yet, I'm just going to say that propane's molecular formula is C3H8. So it has 3 carbon atoms and 8 hydrogen atoms. A molecular formula tells us the atoms we have and how many of each atom there is, but it doesn't tell us what's bonded to what. For that, we'll need a Lewis structure. As I mentioned earlier, organic molecules can make carbon chains. So let's start by connecting all 3 of propane's carbons in a straight line. Then, knowing that carbon atoms prefer to make 4 bonds, we can add enough hydrogen atoms around each carbon so that they have 4 bonds. Lastly, we need to check that we've accounted for all 3 carbons and 8 hydrogens in propane's structure. And more importantly, we need to make sure each carbon has 8 electrons around it. An octet. Remember that each bond represents 2 electrons, so 4 bonds per carbon is 8 electrons. So we're good. Writing Lewis structures for small carbon chains isn't too bad, but drawing a bigger organic structure that shows all of the bonds, hydrogen atoms, and electrons can start to get complicated. And let's be real, we're busy chemists. We don't have the time to draw every structure like this every time. So the first simplification we can make is called a condensed structural formula, where we group all of the hydrogens together next to the carbons they're bonded to, instead of drawing each one separately. That's better, but it's still a bit crowded. So we can simplify the structure even more by removing all the carbons and their attached hydrogens. This leaves behind a skeleton of lines representing bonds, which is why this is called a skeletal formula or line angle formula. In skeletal formulas, carbons are the bends or the ends of the lines, and hydrogens aren't shown because carbon atoms in most organic compounds have 4 bonds. So the number of hydrogens needed to give each carbon 4 bonds is implied. We can take these drawing shortcuts for all kinds of organic molecules, no matter how complicated or simple they are. For example, let's look at a straight chain of 8 carbons with a molecular formula C8H18. That's octane, by the way, but we'll get to naming it in a later video. The Lewis structure of octane looks like this. The condensed structural formula looks like this, and the skeletal formula looks like this. And you can see that, unlike the Lewis structure, the skeletal formula uses zigzag lines to represent bonds, because we need those bends to see how many carbon atoms are in the structure. One long straight line basically wouldn't tell us anything. We'll need to move between these structural representations a lot throughout this series. So given the skeletal structure for isooctane, an important component in gasoline, we'll need to know it translates to this condensed formula and this Lewis structure. But the thing is, organic chemistry isn't just carbon and hydrogen atoms. We have a whole periodic table of elements. We've even got a poster. Though, there are a few main ones that are commonly a part of organic compounds. These atoms in organic molecules other than carbon and hydrogen are called heteroatoms. We always show heteroatoms with the attached hydrogens in the skeletal formula, like this one for the artificial sweetener aspartame. Also, it's sometimes helpful to show the lone pairs of electrons on heteroatoms, because it'll help us think about chemical reactions. Skeletal formulas make it easier for us to focus on the parts of an organic structure that are non-carbon atoms or have double and triple bonds. These parts are called functional groups, and that's where all the cool chemistry happens. We'll be dealing with a lot of these skeletal structures or other depictions of organic compounds. But it's also important to remember that these chemicals are real things that we use on a daily basis. Aspartame, which I just mentioned, is in the little blue sugar packs that we add to our coffee, and this cup is already full of organic compounds that give coffee its taste and smell, and most importantly, the caffeine that helps us wake up in the morning. The whole reason anyone can see this video in the first place is an organic chemical called retinal, a molecule in our eyes that's responsible for turning visible light into nerve signals. And not to mention, most video screens and computer equipment have lots of organic polymers. One important breakthrough in polymer chemistry in the 1970s was how to make plastics conduct electricity. These special kinds of polymers are responsible for lightweight laptops, tablets, and phones we carry around, because plastics are a lot lighter than metals. Also, light-emitting polymers are responsible for full color displays. These light-emitting polymers behave almost like metals, but change colors with different amounts of electricity. Plenty of natural things like flowers, fruits, and vegetables are colored because of organic compounds too. Like beets are high in betanin, a dye that gives them a lovely purple color. Some people don't metabolize betanin, so it turns their urine and feces purple. It's also a great fabric dye. So to bring this all full circle, organic compounds give color to a lot of the foods and other things we see every single day, whether they're fixed with urea or not. I hope you're just as excited as I am about how diverse organic compounds are. We're going to learn so much together. But in this episode, we talked about the origins of modern organic chemistry, how to write Lewis structures, condensed structures, and skeletal formulas, a brief introduction to functional groups and heteroatoms, and how Romans used to soak their fabrics in urine dye to make them pretty colors. Next time we'll work on nomenclature and what to call these organic molecules. Thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody, forever, you can join our community on Patreon.